Welcome to This Explainer. I'm really excited to take you on a journey today. We're going to look at something that literally powers every single aspect of our modern lives, but, we rarely give it a second thought until the lights go out, right? In fact, it's often called the largest machine ever built by humanity, the electrical grid. Today, we're tracing the evolutionary arc of how power has been managed. We're talking a journey from the massive, super rigid traditional grids of the past all the way to the incredibly dynamic, interactive, smart systems of tomorrow.
Okay, let's just dive right into this. Here's our roadmap for the explainer. First up, from Edison to modern grids. Second, traditional grid infrastructure. Third, the challenges of aging grids. Fourth, the smart electrical grid revolution. Fifth, energy storage and exchange. And finally, academic training for modern tech, where we'll see how academic institutions are actually training the next generation to run all this futuristic infrastructure.
All right, let's kick things off with Section 1, from Edison to modern grids. To really get where we're going with smart tech, we first got to drop our historical anchor and see exactly how mass electricity generation was born. So our timeline kicks off in 1882 with Thomas Edison's very first commercial power plant over in New York. Now, this was a direct current system, which had some pretty severe limitations on how far the electricity could actually travel. And that limitation? Well, it sparked the famous 1880s war of currents between alternating and direct current. AC ultimately took the crown, allowing power to be transmitted over way longer distances. It essentially laid a completely new foundation for how the modern world would operate. Fast forward to 1901, and Charles Mers built an integrated grid in the UK. This was a total game changer. It proved the massive economic and reliability benefits of connecting different power systems together. You didn't have to just cross your fingers and rely on one isolated generator anymore. This paved the way for the massive UK national grid launching in 1938. What started as localized, isolated power plants had officially evolved into these massive, synchronized national networks spanning entire countries. And that brings us to Section 2, traditional grid infrastructure. By the mid-20th century, we had established these colossal national grids. Let's look at how this super rigid traditional infrastructure was actually engineered to work day to day.
The traditional grid was built on a really simple one-way philosophy. Step 1 is generation. You've got these massive fossil fuel or nuclear plants generating power, usually way outside the cities near water sources or ports for fuel delivery. Step 2 is high-voltage transmission. Here, power is stepped up to incredibly high voltages so it can travel hundreds of miles without losing a ton of energy along the way. Step 3, low-voltage distribution. Substations near your town step that voltage back down to safer, usable levels. And finally, Step 4, the consumer, you. It's a completely linear, one-way street. The plant generates, and you consume. There is absolutely zero feedback loop in this core design. So if demand spikes suddenly in your neighborhood, that plant hundreds of miles away, it has literally no immediate automated way to know about it and adjust.
To manage this one-way flow, engineers relied on systems like SCADA, that stands for Supervisory Control and Data Acquisition. At the time, this was the absolute peak of grid management. It allowed operators in a central hub to remotely monitor and control the grid using specialized software and telemetry. But, and this is a big but, it was still fundamentally a centralized, human-driven system. Think about it. If a tree falls on a power line, the system doesn't just magically fix itself. It alerts a human operator who then has to physically dispatch a crew or manually intervene to reroute power around the down line. So it was highly reactive, not proactive. Which leads us directly into Section 3, challenges of aging grids. Because that total reliance on rigid, one-way, human-controlled infrastructure, it is pushing this century-old system right to its breaking point today. We are leaving our grid incredibly vulnerable right now. First off, we're dealing with sheer equipment failure. Mid-century infrastructure is just reaching the end of its physical lifespan. Transformers blow, wires degrade. But it's not just rusting metal, it's the outdated system engineering itself. Our grid is meticulously designed for steady, predictable power from a massive coal or nuclear plant. It definitely was not designed for the modern era. When a thick cloud passes over a massive solar farm, or the wind just suddenly dies down at a turbine facility, power drops instantly. Our legacy grids simply lack the agility to balance these rapid, unpredictable energy fluctuations. On top of that, there's a real cultural inertia in operations. There's this tendency for utilities to manage the grid using old, centralized mindsets when the physical reality on the ground has already completely changed. The system basically has a total inability to handle the dynamic, multi-directional energy changes of the 21st century.
So this brings us to the most critical question of this explainer. How on earth do we fix a massive continental-scale machine that was essentially designed and built over a century ago? I mean, we can't exactly just turn it off to upgrade it, right? Modern society would literally grind to a halt in a matter of hours. The answer lies right here in Section 4, the smart electrical grid revolution. A lot of experts actually consider this the true fourth industrial revolution. We aren't just replacing old copper wires anymore, we are giving the entire grid a digital brain. The difference is honestly staggering when you compare the two. Traditional grids are, well, they're kind of dumb. They're one way, completely blind to what happens at the consumer end, and incredibly rigid. Smart grids, on the other hand, are two-way and entirely data-driven. They use the Internet of Things to communicate in real time. We're talking every meter, every transformer, every switch, actively talking to the network. Because of this, if a line goes down in a severe storm, a smart grid doesn't just ring a loud alarm for a human operator. No, it is completely self-healing. It uses automated algorithms to reroute power around the damage in literal milliseconds, which prevents a localized fault from cascading into a massive, multi-state blackout. The underlying technology upgrading all this infrastructure is absolutely fascinating. Let's break down a few key pieces. First, we have the IoT, providing real-time monitoring of every single node in a city. Then, we're using PMUs, or phasor measurement units. You can think of these as ultra-precise heart monitors for the grid. They calculate electrical vectors up to 60 times a second to prevent voltage collapses before they ever even happen. We're also deploying HVDC, high-voltage direct current superconducting cables, to minimize energy loss when we're moving massive amounts of power into super-dense modern cities. And then there's the software side. We have SDN, or software-defined networks. Imagine taking the physical, hardwired switches and routers of a grid and moving all their controls into a secure, programmable cloud. This brilliant setup lets hundreds of thousands of smart meters and energy devices be managed seamlessly on one single digital platform, without engineers having to manually rewire anything on the ground. Moving right along to Section 5, Energy Storage and Exchange. Because managing dynamic flow is so paramount, a smart grid isn't just about moving electricity. It is fundamentally about storing it and economically exchanging it. Renewable energy like wind and solar isn't always blowing or shining, so storage is the crucial missing puzzle piece here. Let's ground all this abstract tech in some very real-world economics. $120 million. That's enough to make anyone's jaw drop. That is the amount of money saved annually by the Tesla Hornsdale Power Reserve down in Australia. By using a massive lithium-ion battery facility to store excess energy when demand is low, like, say, in the middle of the night, and then discharging it back into the grid during peak afternoon hours, they have dramatically stabilized the local grid. They balance loads instantly and save consumers an absolute fortune in peak generation costs. That right there is the sheer economic power of modern grid-scale storage. But it gets even more personal with something called transactive energy. Imagine you've got solar panels on your roof right now. On a super sunny day, you're probably generating way more power than your house actually needs. In a traditional grid, that excess power might just be wasted or severely undervalued. But in a smart grid, transactive energy allows you to economically interact with the broader system. You can automatically sell your surplus renewable energy back to the grid, or, get this, even bid to sell it directly to your neighbors in real time using automated, decentralized platforms. You completely shift from being just a passive consumer at the end of a long wire to being an active, money-making market participant. How cool is that? Now we have to address Section 6, Academic Training for Modern Tech, because we really need to focus on the human element here. With all this incredible decentralized digital technology coming online, who is actually going to build, operate, and maintain this futuristic system? This brings us straight to academic training. Our sources highlight Al-Balqa Applied University as a prime example of this exact evolution. Established in 1997, their technical education programs are really stepping up to bridge the immense gap between legacy technology and the incoming smart grid revolution. I mean, you simply can't teach old wiring techniques anymore. The curriculum has to evolve just as fast as the physical grid itself, blending traditional heavy industry with modern networking and data science. Let's look at how this builds directly into the coursework of their Electrical Equipment and Installations Diploma. It's a comprehensive 72-credit-hour program that reflects this exact industry shift. These students aren't just learning how to connect a basic circuit.
They're being trained to diagnose complex digital faults, apply strict international codes, and master both traditional industrial installations and the absolute intricacies of modern dynamic power grids. They are quite literally being equipped for a hybrid world. Think about it. A modern technician might service a traditional mechanical fossil fuel plant on a Tuesday and then troubleshoot software issues on a decentralized, automated smart microgrid on a Wednesday. The education just has to cover both the mechanical past and the digital future simultaneously.
The evolution of the electrical grid from Edison's one-way street into a dynamic, self-healing, two-way network is honestly one of the most exciting and critical technological shifts of our entire time. It completely changes our fundamental relationship with energy. So I'll leave you with this final provocative thought to take away from our explainer today. As this cutting-edge technology reaches your neighborhood, in the future two-way grid, will you just remain a passive consumer, or will you become your own power plant?